Hello, how are you doing?
Hello.
Hi. Last lecture, last unit. And then after this, we're going to do final review and lab. No more labs this week.
Okay.
So we're going to cover the last two chapters, 17 and 19 today, if you want to take a look at the notes. And then also the assignment. So let me open up my notes here. We'll start in about a couple minutes. Just get everybody to join us. So if you want to download your notes, I think I also published the PowerPoint presentation from the book. If you want to take a look at that too, it's similar. And then also download the assignment. We're going to talk about recursion today and data structure in C and assembly. Okay, so I'm going to go ahead and get started. I think more people will join us shortly. So this is going to be the last official lecture for this course. You made it to the end. Congratulations. We still have a few more things to accomplish in this class. The things that we need to do this week is going to be working on our quiz. The last quiz is going to be, or actually the quiz review. So that's the game. And then I will open up the quiz next week because we are going to just work on our assignment and our project this week. So there will be no lab on Thursday. I want you to use that time to start working on your project. So we finish up all the lab that's required for this class. Next week on Tuesday, I will go over the final review, and then that's going to help you prepare for the final exam. And again, there will be no lab. So Thursday is when we're going to use that time to work with our group on our course project. Okay, so that means that I will expect your project to be completed on time with all the required areas. And even if things don't go as planned, you still need to submit the project parts for credits. If you don't complete the project for some reason, whatever parts that you complete, you need to turn that in, okay? Because if you don't, you're gonna take a hit on the grade. I do not take late project, not even a day late, okay? Because we have spent I've given you time, and we've spent a lot of time looking at how we can solve some of the problem with the project. So we need to make sure that it is on time. So right now, what I'm going to do is I'm going to go over the last set of notes, which is unit 12. You can find that on the module here, and then also the assignment. Okay, so make sure that we work on preparation for our quiz for next week. And then on Tuesday next week, I will go over the final review. If I complete it in one session, then you don't have to be on Zoom the following week. I will give you time to work on your project. I will sign on Zoom in case you have questions. Sometimes groups would pop in and ask questions because they can't come into my office hours. but I will leave Zoom on. And so if you need help or have questions, make sure that you see me during those sessions. Regular class time, starting with Thursday this week and then the following Thursday, okay? All right, so let's take a look at our notes, and our assignments this week. So this is going to be on chapter 17 and 19. We are going to talk about recursion in C and data structure, and how that can translate to LC-3 in assembly. As you learn in some programming classes, I know that your programming classes address recursion. Sometimes you would go a little bit further in programming classes, but a recursive function is simply used to solve the task by calling itself. That means that you define a function, and when you call the function, it's a function that calls itself. So to really build out the result, it needs to return the value and take that return value and use it in the operation of the execution of itself. So if I'm doing a running sum, in order to get the actual sum for the next round, I have to get the result from the sum and then use that value in the operation for the function to output the next result. Okay, so recursive function is a function that calls itself. And normally we would use recursive function in place of iteration. Instead of implementing a loop, you can use recursive function, and sometimes you can nest a loop or condition inside your function. Now, you often see the example that's shown here is that I would use a recursive function to do a running sum. So for example, if you are creating a shopping cart in your application, and as it goes through and add each of the item in the shopping cart, right? We can implement a for loop, or we can use a function, and as it adds each of the item, it's going to call itself. So now recursive function has pros and cons, as you know. The positive side is that it is very simple to implement. There's not a lot of requirement in recursive function. It simplified your program. In the larger, when you're building out, for example, in a running sum, if you need to sum up a lot of numbers, you will find that the program is performance is gonna be a little slower, because later on it has to use some kind of memory space in order to set up the calculation of the current calling function, and then to be able to output that. So it needs to store that value, the return value, and then retrieve it or fetch it and use it in the next call. So sometimes when you do that, you would find that it would return a memory address instead, because it's not able to produce the value, or it would be a little slower. So performance has then become jeopardized. But however, right, in mathematics, a lot of the time people prefer to use recursive function because it is easy to read, it is easy to implement. So when you solve problem, a lot of the time you see that scientists and people prefer, on the programming side, they will prefer to implement recursive function. However, we want to know how to do it. Okay, so if I need to keep adding the value to give me a running sum, that means I'm going to sum up, right, the values from the beginning to the end, or I would use the previous value to add to the next value. So we would then define the function as running sum is its name, and it is accepting integer, so it's typed as int. And then in your parameter here, this is going to be int n, that's going to be the variable that's passed for that function. Now in the function, we would then implement a condition. If n is 1, return 1. Else, we are going to return n plus the running sum of n minus 1. So it's going to take the previous value and add it to the current value. And so that way you would have accumulated sum throughout. Now, when you break it down into the diagram here, right? So your result, let's say that we are doing the running sum of 4, it's going to return, right? 4 plus the prior number, which is 3, 2, and 1 added, okay? And then we would, so it needs to be able to calculate the prior numbers addition. So 1, 2, 3, and then add it to the 4. So as you can see, the process in this is that we have to make sure that we have a result produced by calling the running sum of 3, right? Add it with the return 4. So that way we would have the running sum of 4. Now, so it would utilize memory allocation to be able to do that throughout. And as its name, right, it is a recursive function. It's the function that calls itself. So it has to do the running sum of 3, the running sum of 2, the running sum of 1 in order to get to the running sum of 4. Okay, so that means that it has to store return value for the running sum of 1, return value for the running sum of 2, return value for the running sum of 3, and eventually from those values, it's then going to be able to give you the return value for the running sum of 4. Now, this is only going to be 4 numbers, so it should be able to produce that quickly. And we have to think about how our resources are being used. So when you use recursive function, right, you're using temporary memory, and these things get pushed onto the stack. We talked about that in the last few weeks, as your function is being called, and then the variable that's being used in that function. Another example that you often see is going to be the binary search. And in binary search, your array of numbers is divided into half, right? So if I have 100 numbers that I need to, and I need to search for one number, then that list of 100 numbers, or that array of 100 number, is going to divide it into half. So it's going to cut it at the 50th number. And then after that, we're going to size that down to another half. So the first 50 is going to be cut to 25 and 25. And then the second 50 number, from 51 to 100, it's going to then cut into half again. And it's going to keep doing that until it gets down to the single value, right? So it's keep halving the container until it gets down to the single value. That's how it's able to search. And binary search is going to be one of the faster algorithm that you would see for the search mechanism. So when we implement this in C, right, let's say that we have to, if we go back and read this case, if you have a sorted, right, container that contains exams in alphabetical order, and you need to find the exam for a certain student, what that's going to do is we're going to take this list of exam, and then we're going to find the middle point. So we're going to cut it in half. Then we are going to size it down again. So that means that it's going to do the comparison with the match. So here it gives you the overall pseudocode. It's going to look for the exam halfway in the pile. So the first half compared to the second half. If it matches the name, then it's done, right? If it's not, it's going to keep looking, and we are going to compare based on the alphabetical. So if we are searching for students' first and last name, right, it's going to look at the upper half. And then if it doesn't find it there, then it's going to look at the second half. Okay, therefore, we would have the name binary, as it would divide it into 2. So in this now, we can implement, right? We would have a function called find exam, And the variable that's being passed is going to be your student name, the start, and the end. Okay. So your halfway point should be the start and the end divided by 2 because we have to find the middle. And then from there, we would implement the condition. If n is less than start, right, we would use exam not found. Else if, right, student name is name of the exam half point, then we are going to say exam is found. Okay, and then we can implement additional condition. So when this function is called, then it's going to go through and it's going to check because we're using if else, right? So it's going to see if this condition is true. Then if it's not, it's going to skip this part, go to the else if, right? Check this condition is true. If it's not, then it's going to go to the next one and so on. So this is how you would be able to implement, right, a binary algorithm. And remember that this is not just one way to implement. There are other ways, but a lot of times this is the common way, is to take your container, find the middle point, and then do the comparison. Okay, so at the end, what you would see is for the else at the end here, right, it's gonna look so we're gonna call find exam again, and we're gonna pass student name half point and so on. So it's gonna keep doing that, and as we do that, we're gonna section it down to the smaller half and the smaller half and the smaller half until we get to the single item in that container, so that way it can do a match. And in order to do a match, we're using the condition statement here, right? And then looking at the student name compared to what would be at the half point, assuming that we have this sorted already. So if you don't have a sorted list, then you can use, right, a built-in sort function or method to be able to do that, or you can write a sort algorithm where so binary search is effective if it is pre-sorted. Okay, so you have to implement the sort with that. And in the prior week, we also did Fibonacci. And Fibonacci is a sequence that we can build out by using the 2 prior numbers. So we would take the first and the second number and we would find their sum. And then we would continue to do that to build out the sequence. And sequence is definitely different than series in that sequence are just a group of numbers that will be in a certain pattern, where series is a sum of a sequence. Okay, and some of you already took my CIS11, so you already knew that. So in Fibonacci, if we write it in C, right, we would give it a name. So in this case, we're going to call it Fibonacci. Sometimes you would see it right, like fib. This is going to be typed for integer, and we are going to pass int to n. And so remember that Fibonacci, we would have to start either, we would seed it at 0 or we can seed it at 1. So in this case, we would need to implement the condition for the seed. So we would say that if n is 0 or n is 1, we're going to return 1. Else, we're going to return, and then we're going to use the same function. So it's a function that calls itself. So we would have Fibonacci of the n minus 1, which is 1 number previous, plus Fibonacci of n minus 2. So 2 numbers on 2 number in the previous place. So we would have 1 number from your current location to the n 2 number place from your current location. So we would take the 2 prior numbers, add them together to give us the current number. Okay, so here you would see that recursion is implemented for Fibonacci. Okay, and you can do the same thing with Lucas number and other type of numbers that use, right, the n minus 1 and the n minus 2 number, or even some cases n minus 3. So let's look at Fibonacci as far as stack, okay, and how that would correlate to LC-3. So when the main calls Fibonacci, for n of 3, right, you would have fib 3. So that gets pushed onto the stack. And remember, R6 is going to be our stack meter. Okay, so it's going to load this onto the location for stack, which is hex 4000. Now, in order to compute Fibonacci of 3, it needs to compute Fibonacci of 2 and 1. So that means that those get added to the stack too. So as you push them in, so if you look at the manual process in this, when we use Fibonacci 3, when we call this, it needs to call 2 and 1. So that means that it needs to push the fib 2 and fib 1 onto the stack. And so fib 1 is going to be the last push, okay? And that's going to pop first. So whatever the variables, right, that goes into your fib 1, that's going to push last. Okay, and then fib 2 prior to fib 1 and fib 3, that gets pushed first. So it's going to pop last. Okay. So here in the notes, we can see that when Fibonacci is invoked, that's the function. Your activation record is pushed onto the stack. We talked about this before, right, last week. So on your activation record, you would see that your past variables on there and your local variables get added. So, and because it's using the same function, the function calling itself, right, then it also get pushed onto the stack. Okay. So as you see, as you run your program, your stack is going to grow downward. Okay. So it's going to increase. And then as it return, right, as it return, what's going to happen is, you know, as soon as it sets up for the return, the address get loaded for the next call. And so that's when it's going to pop. Any question? Okay. So here, what you would see is it would show you, so when we return Fibonacci 1 returns, then 2 is going to get called, right, for Fibonacci 0, and so on. So your R6, it's going to move up when we are pushing in, right? And then we're going to move it down when it's popped. So as you return and then it does the next call, okay, it's going to move down 1 and it's going to set up for the next call, and then so on. And then eventually, right, if your program complete, because for Fibonacci, it can go infinitely. Okay, so we can keep going and it's endless. Or if you're looking at a partial sequence, that means that we can say, okay, we can go from the first value to the 80th value. So when it gets to that 80th value, right, after it returns, it's going to pop off and we're back to main again. And so this is where we start. Okay, so your R6 is then going to be back to main. So in this class, you have to really visualize how recursion is implemented at the low level. This is the whole point in seeing, right, your register on how it's really pointing, or it is at a certain location, or it's pointed to a certain location on the stack as the stack grows and shrink. Okay, because this is what the processor is using to be able to compute or execute your function. Any question? Okay, so let's answer some questions.
Professor, I have a quick question.
Sure.
Going back to the function definition, where it's returning the 1, are we saying it's returning true at that point if the 0 and 1 are inputs?
Yeah, so if it, because those are going to be your seed value, right? There are no numbers before them. So if your first number is going to be 0 and your second number is going to be 1, we don't have the sequence. The sequence begins on the third number for Fibonacci, right? Because we have to take 0 plus 1 to give us the next number, which is 1. So if the value is going to be 0, then it's going to return 1. That means that it is the seed value. It's not going to be, there's no values before it. So your sequence doesn't start until after these numbers. That's what we're saying.
I see.
Okay.
Thank you.
You're welcome. Okay. So let's come back to the assignment. Let's answer that first and then we'll move on. So in the assignment, we are asked to define what is recursion. And I wanted to expand on this a little bit compared to what the notes and the author's notes is giving you. It is a method of solving a problem where the solution depends on solutions to smaller instances of the same problem, requiring the functions to solve the task by calling itself on smaller pieces of data. Okay, so when it calls itself, it has to produce the result in order to use that result to solve solve the problem in the next step. And the example we looked at is Fibonacci. We also looked at running sum. Factorial is another good example. And random number generator. The one that you've done was using a linear conclusional function, but you can definitely use recursive function to be able to produce random number. So in the lab manual that was written by the university, if you follow it and if you continue it, you can look at, I think there's 1 or 2 more lab at the end, a little bit more elevated from what we've seen. So I think the next lab after that lab is going to be on a recursive function and all of the listings they give you there. So you can attempt it and see if you're able to solve it in LC-3. You can write it if you have time, go back and take a look at it. And you can use it to practice if you wish. Okay. Then for number 3, we would say that it asks you to describe how recursion can be incorporated in programming. What happens on the stack and what is contained inside the activation record. Okay, there should be a question mark here. So when the recursive function is invoked, the new activation record is pushed onto the stack. Once the value returned from the first call, it is used in the next function call. It updates the activation record for the push before the next call. So after the next call takes place, the activation record is updated, then pop from the stack. Okay. So similar to what we talked about in a regular function, the function that is not recursive, right? You still use the activation record and you still push right onto the stack. But because instead of going into a different function, we are calling the same function continuously. So that means that we're still going to use the activation record. We push it onto the stack. We would return it from the first call, then use the return value in the next function call. Therefore, that value needs to be updated in the activation record, then also push onto the stack for the next call. So it's going to keep coming back to the activation record, and it's going to update the values for the activation record in the next call. And we can go infinitely in recursive function, right? For example, in Fibonacci, we can go forever. But if you're looking at a partial sequence, then it will eventually stop at that position for that sequence, like the 80th value. Okay. So as it does this, after the next call takes place, it would then update. So when it gets to the 80th value, it would update the activation record, and then it's going to pop from the stack, right? And then eventually it's going to be at main at the 80th value. Okay, so push, pop, push, pop, push, pop, right? But in order to get to the next one, it has to push the prior and then obtain the value, update the record, push for the next call, and pop the prior, and so on. So it has to do that throughout in order to get to where you want it to be to produce the result for our problem. Any question? And so understanding this, the next time you write recursive function, you can see, right? You can see, okay, this is what the processor is doing, and this is what happens in memory or storage. And so it makes sense on, you know, how we use a variable, because variable or container is just a label to a location of memory. Software is about using memory and accessing it for data and use the data for computation. Okay, question. Okay, so I'm going to come back to notes here, right? So let's look at Fibonacci with the activation record a little closer. So last week we talked about temporary location, we talked about return address, return value, and dynamic link. And so you know what those are by this point. So your activation record, it is used for bookkeeping purposes. So your local variable, right, is going to be here. And then your argument is going to be here, right? Together, they are going to be on the stack. Also, your dynamic link, return address, and return value, that gets added to the activation record, right? So when we push that onto the stack, these things go onto the stack. Okay. Now on C and C++, using C and C++, your compiler does this for you. In assembly at the low level, like LC-3 for ISA, you have to manage this. Okay. So when you write assembly program that uses a compiler, right, that the stack part gets taken care of. So in the newer language like ARM or ARM64, it uses C compiler. So the stack is being handled by the compiler. But if we use assembly language that doesn't use a C compiler, then we need to manage our memory allocation, how our stack is used, and so on, and our data structure. Okay. So here gives you the visual for that. Any question? Okay, so you saw a version of Fibonacci that we did for the lab without all the extra pointers and stack piece. Okay, this code right here is for Fibonacci with implementation of stack. Okay. And we're skipping some of the beginning pieces. So this is just a snippet, just to let you know. Okay. And here we would see how we would use register to register. So it's a little bit different than your load and your store that we normally use in our lab. Okay. So where we start here is the definition of Fibonacci. Just like how you say int Fibonacci in, you know, and then your parameter or your argument is going to be int n, and then you would define your function. So here's the definition for your Fibonacci function in LC3. Okay. With the implementation of activation record. Okay, so this remember R6 is going to be your gauge, right? So we are going to use it to really see what was pushed and what's popped. And so we would add -2 to R6 because we want to push the return address to R6, okay? And we're also going to push the dynamic link. Remember that you're doing this part right here only, okay? So we're going to make sure that we have the return address, which is here, and we're going to do the dynamic link, and then we are going to do the value and then these, okay, for the activation record. So then what we need to do is we're going to take R6 and we're going to store it to R7 because R7 is where it's going to go to be able to return. So we are going to take R6 and store it to R7. And then we're going to move down. So we're going to take R6 and subtract 1. So we are going to push now the dynamic link. Okay, so if you visualize that on the last image, you can see, right? Return address and then dynamic link. Then we're going to store that to R5. And then we're going to move down 1 again. So we're going to add -1 to R6 and then put it on R5. So that's going to be our frame pointer. And then we are going to use -2, add it with R6 and put it on R6. That's going to be the memory location for your locals and your temp. Remember the int n is going to be what's passed, right? And then your locals variable. So this piece right here is just setting up your activation record storage locations, right? Using registers. Then because we are using n, right, in our arguments, we're going to load n. And remember that it's already on the activation record and it was in register 4. Okay. So we're going to initialize the value for n, and then we're going to load it onto register 0. Okay, so register 5 was where n is, right? We're going to initialize 4 and then load it onto register 0. And so after this, we're going to branch it for 0 to check for the case. Why is that? Okay, sorry for the whiplash, okay? But coming back up to what Emmanuel was asking, we have to implement this now, okay? Because when you define a function, right, int Fibonacci, int n, that section for your activation record in LC3, that happens for this line, okay? So the compiler does that. Well, it set up the activation record. Okay, now we're going to handle this part. If n is 0 or n is 1, return 1. So now coming back down here, this is why we're branching. Okay, if we branch for 0, right, and that will be fit base because we got to check for is 0. And then when we subtract 1, when you subtract 1, when it branch for 0, you're going to return 1. So we're going to be also branch for 0 there because it's going to check here. When I take 1, subtract 1, that's going to be equal to 0. Then I return 1. So we're going to branch for 0 with fit base. Any question? All right. So now what we're going to do is we are going to access, because earlier, right, we set up our n. Now we're going to read the parameter, which is going to be your int n. Okay, so we're going to load again your argument. okay? And then we have to represent what is n, which is our current value, and what is n minus 1, which is the value that's prior to n. So if this is n, right, and n is at 0, or register 0, then we would take that register 0, subtract 1 to represent n minus 1. Okay, so this next line here allows you to set up n minus 1. So then we are going to push n minus 1, and we got to move the location by subtracting 1. That means we're going to push, right? So R6 is now subtracting 1, so it's going to move down. Then we're going to take n minus 1, which is in R0, and we're going to store it to R6. And that's how we can get it to the stack, right? So you set up the space, then you move it to that space by storing. Then we're going to jump to subroutine Fibonacci. We're going to call here. And it's calling itself, right? Because it's going to keep doing that, as you saw that in the C. Then now we are going to pop. So you store here to load to get it on the stack. We're going to pop. So push is store. Now we're going to pop. So we're going to load. So we're going to take R6, which has n minus 1, and load it back to R0. Because when we push, right, we subtract 1. So when we pop, we add 1 to R6. Okay. Now we are going to take our temp, which is in register 5, and we're going to start to register 0 with a -1. So we're going to store the temp, and then we're going to read the parameter. So we're going to load, okay, with a 4, and then to represent n minus 1, just like how you did n minus 1, I'm sorry, n minus 2, we are going to now take register 0, which is n, and we're going to subtract 2 or add -2 to represent n minus 2. And then we're going to push n minus 2. So now you are 2 numbers prior. So n minus 2 is then pushed onto the stack. And then we're going to store it to register 0, and we're going to call. Because it needs to take, right, the 2 prior values, sum them to get to the next. So it calls itself again. So this section right here lets you add n minus 1. This section right here lets you add n minus 2. And then when we finish the n minus 2, just like the prior section, we're going to pop. Okay. So load to register 0 from register 6. Because we store it to register 6, now we're going to load it to register 0. Then we're going to add 1 because we subtract 1, right? We move up, now we're going to move down. So we're going to load the temp. And remember, temp was in register 5, and we're going to put that onto register 1. Now we got to combine everything. So everything, the R0 was for the R0 was for n minus 1. The R1 is for n minus 2. You add them together and put it on register 0. Then we can branch -0 or positive, and that will be the n, right? Assuming that we're doing a partial sequence. So it's going to check for -0 and positive. So this is like using unconditional branching, because it's going to check for all the flags there. Then for your base, we need to return 1. So for the return, that was in register 0. So we just add 0, or we clear 0, and then we add the 1 to return 1. And since we branch to fib n, right? Fib n here simply pop everybody from the stack. So you are going to store register 5 to register 0 with the 3, okay, because it's 3 location up. And then you are going to pop the variable, which is in register 5. You're going to pop the dynamic link. So you're going to load it back because earlier you store it when you push. So you load it back. And then you are going to add 1 to register 6 because earlier we subtract 1 from register 6. So we're going to move it back up. Okay. And then we are going to load register 6 to register 7 because earlier we stored to register 7. So now we're going to pop the return address and then move it up 1 space again. So add 1, then return. So this section, right, is handling the pop from what you did earlier at the beginning when you push. So it is the opposite. Okay. Any question? I saw something in the chat here. Is this total sum stored in R0? Yes. At this point here, right, before the branch and ZP, your next value in Fibonacci is in R0. So if I take 0 plus 1, I get a 1, right? That 1 is in register 0. Or if I take 1 plus 1 equal to 2, right? That 2 is in register 0. So yes, your sum is there. And in the base, we clear it and we add the 1 to return 1 in the case that if it is 0 or 1, the seed values, the beginning, the first 2 values. You can seed it at 0 and 1, or you can seed it at 1 and 1. Okay. Fibonacci, you can do 0 and 1 or 1 and 1. It's still going to give you the same sequence. A lot of the times you would see that they seed it at 1 because it's easier to write in the condition, right? If n is equal to 1, return 1, right? In the case where if you seed it at 0, you have to say if n is 0 or 1, return 1. Okay, so that will be just a choice for the developer. I've seen a lot of people just use seeding at 1 for n minus 1 and n minus 2. Okay, question. Okay, so next let's talk about data structure. So that will be chapter 19. So chapter 17 review some of the things that you've learned prior, but we implemented recursive function there, so you can take a look at it closer. And you can definitely implement recursive function for your project, right? More power to you if you do that. Okay, but you don't have to. I didn't require it. You can just implement subroutine or function in your project. I will be happy with stack implementation and all the criteria that's met. Okay, so data structure is a way that we can organize data in memory, and you spend CIS11C in that course, right? If you took that course, you spend the entire semester, the entire course talking about ways to manage your data, organize your data in different container, but mostly using pointer in C++, okay? Because data don't really move around. We just find a more efficient way to point to the data. Because data is stored dynamically, so it's just gonna throw it in wherever it could find. And then we just find a quicker way to access the data by pointing to it, okay? So data structure can be divided into struct or linked list. And struct could be a type as well, okay? So when you see data structure, it could be a struct or a linked list. And in C++, you can have a doubly linked list, right? Where it is both ends is there, it's accessible. Singly linked list is only one side, and so on. Okay. So a struct is a mechanism that we can group together related data items. That could be different types. So I can have int and long and double together. Okay. Because if you're looking at an array, if you define an array, you would have int array 1, for example, right? It would just only be type int. So we have to find a way to group the data that has different type together, and we would use struct in C or C++. So the example that they use here is for airborne aircraft, and we want to, let's say, create a program to calculate various things for the aircraft. Okay. So you would have char as a type for flight number, and that would be, it would hold 6 characters, right? Because null termination to represent for the string. So flight number, your int altitude, longitude is going to be integers, latitude is going to be integer, your heading is going to be integer, and your airspeed is going to be double type. So when we define your struct, it would look like this. Okay. And so in C or C++, you would say struct as a keyword, and then its name, flight type. And that would be meaningful to what we're using here or our program, right? And then you open your curly brace, and then there you would define, okay, flight number, and so on. So you see a mix of things in here. Sometimes it could also be the same. You don't have to have different types, but structure or struct, right? You can include different types. So you would have container in here that would use different type. And then we would enclose that with the curly brace and close it out with a semicolon. So that's C. So take this in the aspect, now the perspective of the memory, this is what it looks like. Okay. So that means that your character, remember your char is going to be 7. So it's going to go from 0 to 6 for the indices here. So the first one here is going to be the first character. And this is going to be the last character. So it's going to section, right? One word. Remember when we did day of the week, it talks about Sunday, right? That's why you guys have to align everything. Otherwise, it's going to offset the character. So we would use one word for each of the character. So here is 0, and this is 6. That gives us 7. Then you would have the altitude, right? That's part of the data structure. So that's going to also take up one word, longitude, latitude, heading, and so on. So these variables get added as well. Okay. However, right, I did not like this. This overall visual is okay, but there is a misleading part in here, because you should ask me, well, what happened to the double airspeed, right? Okay. See how they section two words here? Remember in the last week, we talked about how if it is a double, right, we would take that word and multiply it by 2. So that memory location is double. Okay. So this should visualize based on the type that you would define in C. So as we would have double airspeed, you got to make sure that you have 2 locations sequentially, right? So we would say that the compiler would set up the area of the memory depending on the members. That means that the type, right, that you define for your members inside your struct, like airspeed, heading, flight number, and so on, it would set up the location based on the size of data that you need. It does not allocate the memory of the struct, but it really sets up for the members only. Okay. So when we define the struct, it depends on what's inside the body of the struct, which is going to be your members. That's going to be setting use as a reference for memory location. So your memory is allocated for the individual members inside your struct. Question. So let's talk about the next part here. So the way that you define this is you are going to type it, right? And then give it a name. Okay, and then inside the body of your struct, you would just then define your member variables. So let's look at this now, because now we gotta translate it to LC-3. So let's say that we have int x, flight plane, int y, and then we initialize plane dot altitude is 0, right? So we would then clear register 1. We would take register 5, which is going to be your variable for plane, this part. And we would subtract 13. Any idea why we're subtracting 13? If you look at the physical, if you count this, right, it is an array of memory. We're setting up that array. Okay. So for the 8th word, that is going to be at 7 because it's 0 to 7, right? Think about the physical array of the memory. So we're going to store, so register 0 has our plane. Okay. So we're going to take register 0, which has the plane, and we are going to add 7 to it and store it back into register 1 because we cleared that earlier. So that's going to be the 8th word. Okay. So your int x is register 5, right? And you have to set up int x, int y, and then plane dot attitude is 0. So at the 8th word, think about the physical location. That's going to be where your plane is going to be. Okay. So you always think about how the members or your members in your struct is going to be at a certain location in the memory or a location in an array of memory. That should be more closely to what this is referencing. Okay. Question. So for this structure, we just need to set this up, right? And then to really access specific data that would be for the members, you just have to make sure that you store from the actual location. And that's how you implement data structure in assembly. Okay, so let's define this. For number 4, it asks you to define data structure in C. And we already saw this in the notes. It is an organization of data in memory that group related items together. And related item doesn't necessarily mean the same type, right? And when it does that to really achieve the programming convenience and efficiency. Yes, we don't have to organize our data, but when you organize it, as you see how it allocates the space, the compiler does that. It is definitely more convenient for it to use that section of the memory just for the structure. So 5, what is a struct? It's a mechanism to group together related data items of different types in C and C++. And so at the higher level, when you write the struct in your other classes, now you can actually see what the compiler does when you define a struct in C or C++. Okay. So an example that I put here is we would have struct and we would say food. Okay. And then for our members, we can have double weight, double price, string description, its size, string color. You know, there are many things that you can describe food. Okay. It could be that we would use, right, the structure to compute food costs or do a shopping cart for customer when they buy food, right? Like if I buy beans, I would need to measure by pounds, price per pound, and so on. Any question? So when you implement, you should always think about how you can implement data structure in your program. Okay. Especially for C, C++, Java, object-oriented, right? And then you should always think about how you can, for C++ and Java, you can think about classes, right? C is not object-oriented. C is different than C++ in that, right? But if you learn C++ and Java, right, you learn data structure, you should always write your program with data structure and classes, okay? Class object. Okay, questions regarding 4, 5, and 6? Okay, so let's talk about malloc. I touched a little bit on this with my classes, my CIS7, but I'm going to come back to this in this class because some of you took my CIS7 and some of you probably use memory allocation from other C++ class. Okay, so we saw how we can set up the array for struct, okay? And so if you are looking at defining an array like this, flight planes array, right? Remember flight planes was coming from the struct, and that will be 100. Okay. So each array element is a struct. Okay. And based on what we used earlier, that will be 7 words in this case, because it's 0 to 6, right? So to access the member for a particular element, you simply use the index. So planes 34.altitude, right, is this value. So if you see that in C, we would simply think about how we can point to that. Okay. So here it tells you that the operators are the same in the present. It's going to be from left to right. So if you need to access a specific index, you would just use the index value. Now, if you implement pointer for struct, you just simply declare it. And just like any container, you would use an asterisk, right? And then give it a name, plain pointer. And then assign it as a reference. Okay, so plain pointer is going to be reference, plain, and the index value. So once you declare it, you can use it. Okay, so we can do it this way. We can do it this way. We would use a pointer. So to access the member, it's gonna be using the struct address, right? It's pointing to the address. Okay. So the dot operator has higher precedence than the asterisk here, right? When you look at that, even though it's going from left to right, right? This is not going to be the same as this is not the same as this. Simply, if you put the parentheses around the pointer, right, you would see that it is different. Okay, for C. Okay. Question. You can also pass struct as arguments, right? Flight was our struct. Okay. And we have used plane as the pointer, so you can definitely do that. So it says, unlike the array, the struct is always passed by value into a function. That means that the members are copied to the function's activation record. Okay. And changes inside the function that are not reflected by the callings routines copy. So it does not update. Okay. Because it has a when you call the function, the variables inside the struct is added to it's pushed onto the activation record, or the activation record's pushed containing those variables. But when you use it inside the function, if the values are updated, right, it is not going to reflect the routine's copy. Okay, so this is how it's written in C. Now to continue the example, they talk about dynamic location here. Okay. So if we can't allocate an array and we don't know a certain value for the planes, then we shouldn't cut up a space in memory because we're uncertain. Okay. So what we should do is we should only allocate storage for data as needed, meaning that dynamically. And in C, you can use malloc or malloc. This is memory allocation. Okay. So this is a function that allocate memory at the runtime called malloc. What it does is going to cut a region or a section of the memory where it would be contiguous together. Okay. Depending on the size in bytes. So when the bytes are allocated in that section, it becomes a heap. And some of you already know this. Okay. So in a runtime, your runtime system tracks different chunks of memory from the heap. Okay. The way that I always remember heap is heap always pertain to user data. So think about data when you think about heap. And heap is the section of memory. It contains section of memory that is allocated for data. So the visualization of this is like this. And I took this from the internet. Okay. Your stack, right, is growing downward. Your heap is growing upward. Your stack is managed by the compiler, right? At the low level, we see this in assembly. Your heap is managed by the programmer. This is why you should implement data structure. Okay. Then you got the static data. This is where when you initialize your data, right? And then when you initialize your data, you give it a literals, okay? And then you would have the instructions. And these are instructions is the only thing that's executable. And at the low level, you see instruction as add, and, right, branch, jump, and so on. The literals in assembly at the low level are your immediate value, 5, 7, right, hex 5, decimal 7, and so on. Okay. Your static data, this is where you have to define or I guess define certain things, right? Like your labels, things like that. So when you use this, right, when you using structure or you implement data structure, you're working with dynamic data, which is heap. And so if you effectively implement malloc, you need to think about the size of your data. Okay. And all of this would be represented in bytes. And if you're uncertain or it could be changing, then you can also cast it. Okay. So this would allow you to look at it from a flexibility standpoint, where if you're uncertain or if there might be changes in the amount of memory that you can use for your data. Okay. Now, just similar to stack, right? So once the data is used and if it's no longer needed, right, that space is given back. So it's going to be released back to heap for other things. Okay. So that means that when the function, it's going to free up and it's going to pass the same address that was returned to the map. That means that the R6 moves down, right? For the heap section, your register 6. Question. Okay, so let's answer a few more things here. Describe how memory is allocated in a struct. We say that the allocated storage for data dynamically as needed. Use the pointer to implement contiguous memory allocation of members in the struct. So we would use the pointer to implement contiguous memory. That means a region for the members. Like earlier, we saw that for our flight, we would have 0 to 7 for the flight number. And then the next section would be for your longitude, your altitude, and so on. When you have an array of structs, the members are accessed using the dot operator. And then if it is, I forgot to add this, and index. Okay, so you have to use the index value to access specific item in that array, but you have to use the dot operator, which takes the precedence in the case of array of structs. When a struct is passed as an argument, it is always passed by value into a function. And we said that your members are then added to the activation record of the function, but not copied. Okay. So the function activation record is going to contain the members. Or I should say the members value. Number 10, what is a heap? It is a memory location that is writable but not executable. It's used for it's allocated for data type managed by the developer. Question. Okay, so for the last part, we're going to touch on linked list, which is another container for data structure. And, you know, this particular text, right, doesn't touch on DEC. So if you learn DEC and linked list, double linked list in C++ data structure course, like CIS11C, right? This, we're only going to touch on linked list. Okay. And then I'll touch a little bit on the doubly linked list. So if you understand linked list, you should be able to understand double linked list at the abstract level. So data structure is really about, you know, implementing abstract concept in how we access data in memory location, right? Nothing really moves around. We just, you know, we just point to things, or we can go to a certain part of the memory and be able to set up, you know, add values there, move value, take it away, and so on. Okay. So for 11, we can define a linked list as an ordered collection of nodes, and each of which contains some data connected using a pointer. And my analogy for this is like, think of it like a train, right? And they are all connected. So each part of the train, each cargo, right, or each train component have some kind of data. And you would use a pointer to point from the first to the next, to the next, to the next. Okay, you would start with the head and then you would go forward. Question? Okay, so in a linked list, let's come back to our thing here. Each node points to the next node in the list. So you have node 0 point to node 1, point to node 2. Okay. And it can go on further. But the first node in the list is called the head, node 0. Then the last node on the list is going to be the tail. Okay. And it has to be terminated. Now on the doubly linked list, the last node is going to point to the first node. So the tail is going to point back to the head. Okay, that's on a doubly linked list. On a singly linked list, like this one is showing, it's just going to be one direction and it's going to end at some point. Okay, so it's going to end at the tail. And then that's going to point to null where you have to define a null pointer. Okay, so you can look at a program and you can tell quickly whether it is a singly linked list or a doubly linked list by how these are defined. Okay, so if the node on the last node, if it points back to the head, okay, that's a doubly linked list. If the last node points to the null, that's a singly linked list or simply just a linked list. Okay. For those of you who took data structure already, right? I'm sure your professor asked you to write those programs because when I taught it years ago, you know, their final project, they have to implement at least one of the containers. So, okay, so the advantage, it is dynamic in size. It can grow and shrink whenever that's needed. That's the whole point in data structure. You can add the additional node as needed. So if I need to add something between 1 and 2, how do I do that, do you think? How can I squeeze in another one here? Use the pointer, right? So I can add another node by just pointing to it and then take that point to the next one. So if I need to squeeze something in here, take node 1, point to the newly added node, and then take that point to node 2 again. So that's how you can add in the data using the node. Okay, I can also remove. If I need to remove node 1 here, I just take node 0, point to node 2, and skip 1. Okay, so using the pointer is definitely effective there. Okay. Then for using the array, it's just quickly accessed because they are continuous. So here, there's an example on how you can splice, right? So to find a node, you can quickly find it, but then if you splice, you just disconnect the pointer from 1 to 2 and then point to the new node as I described. Okay. How can you make a double linked list, a single linked list? The last node pointed to the null. Compared to a double linked list, it points back to the head. So just use your pointer. And when you change how your pointer is defined, right, that really changed the way your data structure is set up at the abstract level. Okay, question? Okay, so on the last thing, we need to compare and contrast linked list and array in the data structure. The linked list is definitely dynamic. Data is accessed sequentially because, right? Because we go from node to node to node, like a train, we go from first to second to third and so on. And we can add and remove using pointer. Sorry, Ethan, just, I'm getting a little bit of like noise in the back. So array elements, when you're using an array, if you know the definite size, you can definitely use an array, because array, you have to really think about, like, you know, how many elements that you need. So it is size dependent. Each element is accessed using index. So you can go directly to a certain item in your, or element in your array using an index. All elements are accessed using iteration, meaning a loop. You can use a for loop or a while loop to do that, right? Often you see more example with for loop. Okay, so if you definitely know, you know, how many items or elements that you need to have, then you can use array, right? Linked list is something you can implement as a container to grow and shrink. So, you know, you can add more data, you can remove some data as needed. So in the advanced class for C++, you would see, you know, we talked about data structure, or even Java, you hear about data structure. But ultimately, you know, all of this can you can think about how, you know, not inside the program itself, but you can think about how you can expand data in database area, right? But as far as the application goes, think about how your container is used, your pointer, how your data is stored, how it's retrieved. And that is really about, you know, space and time and how your program can be efficient. Question. Okay. So that wraps up chapter 19. Any question? So if you missed at the beginning, there is no lab after last week lab. If you are behind on the assignments, make sure you get those to me. I started grading your class. I finished with unit 10, so I'm working on unit 11 and other things that if you submit late. I will not take any more late assignment after the end of the month, so make sure that you're all caught up, right? This is going to be the time when you have some flexibility, okay? Work on your course project. Okay, so I will be available on Zoom on Thursday. I'll turn it on and I will mute myself or leave it on. And if you pop in, you can pop in and ask questions during class time. There's a quiz review game, so that will be our last review game. Okay, and so make sure that you can go through it and so you can prepare. I will turn on the quiz. I'm sorry, there's a quiz review assignment. There's going to be a quiz review game next week. Okay. There's no more lecture next week, but I am going to use Tuesday to cover your final review. Okay. So by week 14, you should have everything that you need in this class, all the content, and all you have to do is address, right, your quiz. If you already complete that, then your project and your final exam. Final exam will be open during the first, I want to say the week of the final. So I will open it on Monday, okay, at 12 a.m. I guess, and then I will close it on Thursday, which is the last day of our class. So hopefully you will have all your projects submitted, right? Your final exam completed. I do not allow late final or late project. This is why I'm giving you time. So the whole week you can take your final at any time. And then once you submit the final, right, it's multiple choice. So it's going to give you a grade. Your extra credit is going to go in, I want to say after I grade your project, I will take a look at the deficient area and don't expect it to be like, you know, a huge lift, okay? At most about 7-8%. So we should be there here next Tuesday for final review, yes. And all the other class time for the rest of the semester will be like office hour. Yes, that's correct. Yes. So yes. So I hope to cover your final review next Tuesday. And if we can wrap everything up, then we would finish it in that one session. Thursday, use it to work on your project. Okay. And then the rest, yeah, I will be available for help or questions, feedback, etc. Now, if you want me to take a look at your program that you wrote, right? You know, if you show up on Zoom and you give me the file, right? Like I cannot read 150 lines like at one sitting and be able to see that. I can glance over and tell you like, oh, okay, maybe look at this and this and this, or if you're stuck somewhere, I can point you to some area where you can fix, but I'm not gonna be able to like debug the program for you. Okay. If you want me to look over your documentation, that stuff like that, right? Shoot me the file. I will take a look at it and give you feedback. I have some students from CIS11, they already done that. So they asked me like, what do I think about their program? You know, what should they improve? Now, if you submit it, at the end, I do write a little bit of feedback on what you should be doing with your program, or, you know, what some of the things that you need to look at and so on. Okay. Just keep in mind that the GitHub and the evaluation and all of that needs to also be included for your project. Do not wait until the last minute, right? I've had students that like turn stuff in at 11:59 and they have no flex room to submit GitHub or team evaluation. Okay, don't wait. Okay, this is why we have Thursday for this. Okay. All right. Any question? Okay. So overall, right, I love teaching assembly. This is one of my favorite to teach because, you know, every time I teach it, I feel like, you know, the stuff that I've been doing gel for me. And I hope that you enjoyed this class. I really enjoy teaching this class. It comes around once a year for me. And then, you know, and I hope to really see you. This is not our final goodbyes, but I hope to also see you in my other classes. I do have non-credit stuff that's pretty fun. Or, you know, during the summer or the winter, that you are taking my classes online. And, you know, if you have any questions or any concern, or even when you finish my class, you know, if you ever need syllabus for transfer or letter of recommendation, if you did well in my class, you can always keep in touch. I am also on LinkedIn. You know, and if you have questions or anything like that, let me know. But tomorrow I'm going to do a little bit of a session with the STEM Center. I will post that in your announcement after this class, regarding cybersecurity jobs, even for developer or software engineer. So if you are interested in that, you know, you can join the session tomorrow. It's like doing college hour. So I'll post some information there. And then we have a few other events that are coming up. So, you know, just little side activities if you're interested. Okay. All right. So let me stop recording. And then if you are in the summer data science one, I will also work with you, but I think you have your advisor depending on the campuses.